We have another example problem here. We have a uniformly charged sphere that has a radius of 40 centimeters and a total charge of 80 nanocoulombs spread throughout its volume. If the following sections were removed from the sphere, what would the electric flux be through each surface? And technically, we wouldn't have to remove them, just considering the following sections. What would be the flux through those particular sections? So A is a spherical section with a radius of 10 centimeters. B is a cubical section with sides of 5 centimeters. And C is a cylindrical section with a radius of 8 centimeters and length of 15 centimeters. So our actual charged object is a sphere. We will consistently use a capital R to represent the radius of the actual charged object. So the radius of this charged sphere is 40 centimeters. It's telling us that this total charge of 80 nanocoulombs is spread throughout its volume. So somehow in the making of this insulator, we have been able to give a uniform charge throughout the entire volume. Okay, charges spread throughout the volume is a volume or volumetric charge density. Meaning charge per volume. Since this problem tells us this charge is uniform, that means if I take a little section out, so like our little cube, the density, the charge density within that cube is the same as the charge density for the entire spherical charge. So the original charged sphere. So what I'm going to do is I'm going to go ahead and find this charge density. We have 80 nanocoulombs spread throughout a spherical volume. Volume of a sphere, 4/3 pi r cubed. I'm going to put our radius in meters so that I'm getting SI units. Okay, so this will be our charge density. And I forgot my calculator. Let's see if I can figure this out on my phone. Okay. All right, so let me see here. Divided by all right, since I forgot my calculator, I'm actually doing these calculations in Excel, and hopefully I've done it correctly. If so, the charge density for this sphere, specifically the volumetric charge density, 298.42 nanocoulombs per meter cubed. Now again, I'm going to keep a number of decimal places simply because I am not at a final answer. This charge density is uniform. So whether I'm talking about the entire sphere, its charge divided by its volume, or a section of the sphere, the charge within a section divided by the volume of that section, this charge density is the same. It's like water. Whether I have a bucket of water or a coffee mug of water or a swimming pool of water, the density of water is the same. Okay, the reason I want this is now we're coming back and we're trying to find the electric flux through each of these three sections in part A, B, and C. A sphere, a cube, a cylinder. These are all closed surfaces. Also can be referred to as Gaussian surfaces. And Gauss's law tells us that the electric flux through any closed surface can be determined by knowing how much charge is located within that surface divided by epsilon naught, our constant. So let's look at finding these. So A, we have a spherical section that has a radius, I'm going to use a lowercase r to represent this, of 10 centimeters. So if I come back to the top right where I have our original charged object, this had a radius of 40 centimeters, total charge of 80 nanocoulombs spread throughout the entire thing. Well, this sphere, this section we're talking about, is smaller. It only has a radius of 10 centimeters. So if I have this smaller sphere, it is going to have some of the 800 nanocoulombs of charge within it, but not all of it. And so we're trying to find the flux through this smaller sphere. And that flux will depend on and be determined by how much charge is physically located within it. Okay? So Q in this surface, it's not 80, because this 80 nanocoulombs of charge was spread throughout the sphere that had 40 centimeters radius. Q in is going to come from our charge density. We calculated the charge density by the total charge divided by the total volume, but we can always say, if it's uniformly charged, that this charge density also represents the charge within a smaller segment divided by the volume of that smaller segment. So Q in is going to be the charge density we calculated times the volume that we're trying to find how much charge is within. So coming back to this spherical section, we will take our charge density and multiply by the volume of this smaller sphere that has a radius of 10 centimeters. So our charge density we already calculated. The radius of this smaller sphere is 10 centimeters, so 0.1 meters. So I'm going to go calculate this in Excel again. So plugging these numbers into Excel, the meters cubes are going to cancel, so the units I'm coming up with are nanocoulombs, since I left my charge density in nanocoulombs per meter cubed. If I plug this in correctly, we find that the charge in the sphere, meaning this smaller sphere that has a radius of 10 centimeters, would only be 1.25 nanocoulombs. Knowing the charge located within that sphere, the flux would be that charge in the sphere divided by epsilon naught. So 1.25 times 10 to the negative 9 coulombs. Epsilon naught is our constant, the 8.85 times 10 to the negative 12 units. Coulombs squared over Newton meters squared. So plugging this all in, I'm getting 141.24. We have, at best, two significant figures. So 140, the units, one of the coulombs cancels. The newtons meters squared comes to the numerator. And so the units of our flux is newtons times meters squared over coulombs, which hopefully makes sense if we think about flux in terms of the integral of electric field dotted with area. Electric field is newtons per coulomb. Area would be meters squared. Okay, so this would be the flux through this spherical section that has a radius of 10 centimeters. Part B, this time we're taking a cube that has a section, or a side rather, of 5 centimeters. So B, where each side is 5 centimeters. 5 centimeters would be well within the original sphere. In fact, if we come up to my original picture that we can only see part of on the top right, I drew a little box that's big for being 5 centimeters on a side, but we can still kind of think of that as just that section. Well, this similar setup applies. The flux through a cube, because it is a closed surface, depends upon the charge within that surface divided by epsilon naught. So we need to find how much charge is in this cube. The nice thing is we're still going to take the charge density times the volume in. So what we mentioned before, that's charge density, because it's uniform, whether we're talking total charge over total volume or charge within a section divided by the volume of that section, that charge density is the same. And so we can take our charge density and multiply it by the volume of this cube. Well, the cube, all sides have the same length. The volume of a cube is length times width times height. So we will take our 5 centimeters, which I need to put in meters, to end up with the correct units. So I'm finding Qn to be 0.0373 and just keeping some more digits. So this is our value in nanocoulombs. Hopefully it makes sense that we have less charge within the surface. This cube is smaller than the sphere in part A by quite a bit actually. And so we should have even less charge than we did in part A. Knowing this charge, we can now solve for the electric flux through this cube from this charge and from our constant, 8.85 times 10 to the negative 12. Two sig figs, I'm getting 4.2 Newton meters squared per coulomb. Less flux because there is less charge located within that cube. So the last Gaussian surface is our cylinder. Our cylinder has a radius of 8 centimeters and a length of 15 centimeters. So radius, completely enclosed within the original sphere. Volume of a cylinder is 4 pi r squared L. But again, since we're calculating flux, we need to find Qn, and we're going to find it in a similar way. The charge density times the volume that is enclosing that amount of charge. So our charge density is the same. Our volume, though, is what is different. That's in meters. So pi r squared, let me write that better so you can see the meters. And then the length, I also want in meters so that this charge is in nanocoulombs. So if I have plugged this in correctly, the charge located within this cylindrical surface would be 0.9 nanocoulombs. And then calculating for the electric flux through this cylindrical surface. So the 0.9 times 10 to the negative 9 coulombs divided by our constant. (101.69). So essentially 100 Newton meters squared per coulomb would be the flux through that surface. Now, in these situations, the electric field that passes through is not going to be uniform, meaning if we wanted to go back to flux being the integral of E dot dA, which is totally valid, the integration would be somewhat difficult to set up. But the beauty of Gauss's law is that we didn't need to integrate. The net flux through any type of closed surface, that's the requirement right there, is that the surface is closed. That flux is equal to the amount of charge located within the surface divided by our constant, epsilon naught. A very simple solution for finding flux. We are going to look at a few situations where it is possible to work backwards, meaning knowing the flux or finding the flux from the charge enclosed and work back to find the electric field. That doesn't work in a whole lot of situations, only a few, but I will show you in the next video what situations that applies to and how to approach those problems.